Assalamualaikum warahmatullahi wabarakatuh. Hope you are doing great today. Alright, today's session will discuss part number 2 of chapter 15, Oscillatory. So let's get to the textbook. Right, I am on page 392. So let's jog your memory in terms of the understanding. So you are greeted with this figure. This figure shows you how motions of a simple harmonic object that undergoes simple harmonic motion are plotted with time, Now, as it's being plotted, you notice that it follows a sinusoidal curve. Like instant, okay. So as over time, with time, so they are very in position, and it mimics like if you have one cycle where 360 degree occurred, okay, angle covered is 360 degree, and a cycle consists of two small cups or one very large cup, okay, for instance, right, this is one large cup, two small cups, all right, okay, now two small cups, right, right, nevertheless, okay, in what the textbook trying to portray here and try to highlight is this idea of an additional phase constant. This is called 5, where this is actually a phase constant. In physics 1, you learned this expression before, but a bit different, where the expression was given in this manner. The expression was given x displacement, amplitude, cos, similar, but only a product of omega t. There's no 5 given. So why now? Why all of a sudden there's 5? Okay. Number 1, when you use this expression, bear in mind when t is equivalent to 0, use your calculator, set it in radian mode. Let's play around. Okay. So cos 0 is equivalent to 1. And therefore, x is now at t equivalent to 0, x is a times 1. And that's the reason why your graph would start here. And so on. Right. So this is a cos omega t. Now look at what given by your textbook. So there are cases that when object under simple harmonic motion, it doesn't straight away start at exactly positive A. It starts somewhere less than that, or negative A. So in order to remain using this expression, therefore, rather than change the expression into sign, whatever, because you will notice that there are also equation for sinusoidal become sine. And the best method is by introducing correction. So this 5 is actually a correction that equivalent to the angle, right? That's what we are going to see in example number 15.4. But as of now, just understand that it's there because the graph does not start at exactly A, exactly at amplitude. Alright, okay. Now recall a little bit on the idea. What is A? A is amplitude, omega, angular frequency, period is T, where T is tarmac, and also remember that omega itself is actually 2 pi f, and therefore 2 pi over period itself. And here's something to ponder, that F is 1 over period. Okay, recall those things. You are going to see one again. Alright, example of simple harmonic motion. Okay, it's very easy to memorize or understand what object, which object, what are you doing to exhibit simple harmonic motion. The key is this one, oscillate up and down, back and forth, oscillate up and down, okay, vibrates back and forth. Alright, the term back and forth, oscillation up and down, this is what we call as a repeated motion. We call this as repeated motion. Repeat itself. So repeated motion. Now this repeated motion is actually an indicator that it's a harmony motion. Because for instance let's go back to your ordinary life. By 6 a.m. definitely you woke up. You will woke up. Why? Oh, stomach ache, madam. Nature call. But then all of a sudden on Friday, you woke up, there was no nature call. So it's disrupting the pattern, the harmony pattern. So this repeated motion is actually a harmony motion. And it's simple because just back and forth, back and forth. All right. So that's the idea. All right, let's have a look. Example 15.5, 15.1, a block spring system. Okay, what we have here, Intiscape. All right. Okay, now let's have a look. You have 200 gram block connected to a light spring, force constant 5 Newton per meter, free to oscillate on a frictionless horizontal surface. So there's no friction, alhamdulillah. Keyword says when it's frictionless, energy is conserved. It displays 5 centimeter from equilibrium and release from rest. And release from rest. Okay, hold on. I seen one video that shows this idea. If it's here, then it's rezeki lah. Alright, it's almost like this one. So this is equilibrium, displace, and then hold, release. Alright, therefore, between the green and also the black lines, those are the amplitude. Alright, and therefore, let's jot down. This is our A value. This is our K value. This is our mass value. So it's not the mass of the spring. In fact, we assume spring is massless, or else then there will be an additional acceleration, deceleration. Okay. Alright. Okay, the question. Find period of its motion. Alright, I would rather use this tamak lah. Tamak square root M over K, or you can use what given in the textbook itself. So in this case, you find that mass is the 200 gram. Make sure that it's in SI unit and K is 5. The reason, because you have Newton here. Newton is an SI originating from SI product. Okay. Next question. Determine maximum speed of the blocks. Okay, maximum speed of the block is whereby, okay, when we are here, then let me double check. We have seen this previous class where V maximum is on page 390. That it's actually come from the derivative of the expression x towards dx dt, right? So A omega is the maximum, A omega squared is the maximum acceleration as such. All right, now let's get back here. All right, remember yesterday, the other day, that I did mention that the negative will be omitted? Yes. So this is the reason why. For instance, this question is asking speed. Plus, you have no idea whether the object is on its way moving to the right or moving to the left. Remember, for instance, if you are here at the equilibrium, spring object is now oscillating to the right, but then passing through 3 centimeter. It's 5 centimeter is the maximum amplitude. So 3 would be in between. So on its way. So that moment it's moving to the right, but then it's passing through the same position again, but this time around it's moving to the left. So you understand why it's a bit confusing if you keep on using the negative when it's just asking for the maximum value, right? So A omega, just follow suit the expression, you will arrive with the answer. Now, the other expression is asking you, the other question is asking you what will be the maximum acceleration. So you are using this expression, or okay, I'd like you to give this expression a try. KXMA, remember that you can omit the negative, same reason as this one. Just omit, okay? Take it out. So, however, a bit different is X is now being replaced as A. You will arrive with the maximum value of acceleration belongs to the block. Give it a try. The last one, D. Express the position, velocity and acceleration as a function of time. Okay, this is getting back to the idea of derivative. All right, so this is X equivalent to A cos. Okay, the original expression supposedly would be written as X A cos omega t plus 5. All right, let's do a little bit of mathematics. In the case of this object, what happened is at the start of time, when the time is equivalent to 0, the displacement of the object is 5 centimeter, is amplitude. Okay. Since it's already at the amplitude, okay, because of the initial condition that x is a and t 0, and therefore there is no phase different because this is angle, okay, phase different, phase constant. Some textbooks say phase different, okay, so our textbook use phase constant. So that's the reason why this is 0. And it makes sense that, okay, it makes sense that if you put cos 0, you have 1, and then mathematically you have, for instance, omega t is 0 plus 0. Understand? So you have like 1. Okay. So cos 0 become 1. 1 times A is A. That's the idea. And therefore, this expression would be simplified by considering this as 0. So 0.05, this expression is missing something. Should be together with units. Okay, so it should be written as 0.05 meter cos 5t. Okay, I'm aware that they give you 2 decimal place. Not to worry, so long that you understand the concept. And as well, when you do substitute numbers into your calculator, then it really matters that you consider 2 decimal places. Right, the same goes here. So it should be like meter per second, and while here 1.25 should be meter per second. Okay, let's forget about this. Right, let's revisit how we do the derivative. So V is actually dx towards dt. Okay, so we find A times width, the constant to the t, which is omega. That's the reason why it becomes omega A or A omega. Cos becomes sine. Notice that when you go acceleration, sine becomes cos again. Yet when you do the law, okay, go follow through the laws, cos when it turns into sine should be with negative, but sine when it turns into cos would be no positive value, but it brings this negative to this here. So this is dv over dt. All right. Okay, so the rest is just mathematics. Try it out. Right, let's look at example 15.2. Now this time around is more detailed. Consider again the same block as an example. So where position, velocity, acceleration is given in D of the problem. Find general expression for all times that which the block is located at x equivalent to half A. So it's asking you if a system undergoes simple harmonic motion where it's supposed to start at amplitude A 5 centimeter, what should be the general equation for T, so that when you substitute you get the location for X becoming half A. That's the idea. So therefore, what we did is we go back to the general expression just now. So X is A cos omega T. Recall again 15.1. 5 phase constant is 0. Why? Because the system start at the amplitude. Okay, like what I sketched here. Right. And we replace X with half A. And then we simplify the equation T. Notice that in our calculation, we can cancel out the effect of A value, and simplifying become 1 over omega inverse cos 1 over 2. Alright, okay, good. Now, when you arrive here, okay, it should be very helpful if you refer to this common angles, okay. So having cosine 1.2, cosine 1 over 2, it should portray that the radian angle is pi over 3. Okay, pi over 3. Kenapa radian, not degree? Yeah, it's when you use cos theta or sinusoidal expression, it should be in radian mode. Okay, in radian mode. So that's really how you arrive with 1 over 2 equivalent to pi over 3. So this is where the pi over 3. This is where, sorry, hold on. Okay. My line simply disappeared. Alright. So this is our pi over 3 just now. Okay. Being half of it. Okay. Pi over 3. Which is 60 degree. 60 degree. Now by logic, if using our version of understanding, this is one single phase. One single phase consists of 360 degree. So 360 degree, which equivalent to 2 pi rad. So one big cup. Now, if I were to separate them, then this is equivalent to pi. Okay. So exactly here, 1/4 is pi over 2. So most probable if it's half amplitude, the angle involved should be half over 2 divided by 2, right? It could, okay? But pi over 4 lah, it becomes pi over 4. But no, from our calculation, we shows that because this is not a proportional graph, okay, a linear graph. Then our result shows that, oh, being half A occurs at an angle 60 degree or pi over 3. Pi over 3. Okay, understand? All right. All of a sudden, why is it that this one is together with plus 2 pi n? All right. Okay, this is the explanation. Now, bear in mind, they want all the times. The question is asking you all. So when it's asking all, it means that more than one cycle. So more than one cycle. So this now, this is one cycle. From here to here is one cycle. Okay, this is one cycle. This is one cycle. So they want more. Another. What happened after that? What happened after that? Times after that. So that's the reason why they include this expression. This is the next cycle. The next cycle. Okay, next cycle. So if you put 0, it's that first cycle. This is number 1 means the next one cycle afterwards. and then number 2, the next 2 cycle after that. All right, then they simplify, become this expression. However, why all of a sudden we have another second situation? Now, according to this figure, position of that block being at half A is not singular. It's not all alone. It's not just once. It's twice. It's twice, which is here. Which is here. Okay. And what is this angle? Okay, I simplify it in this version. This angle is actually 2 pi minus pi over 3, because this is pi over 3. So on the left side is also pi over 3 as well. So this is pi over 3. This to this is pi over 3. And therefore, from here to here, the angle is 2 pi minus 5 over 3, which make it divided by 3 times 3. So 6 pi minus pi is 5 pi over 3. So that's right. And then again, we add the next cycle. So simplified, you have the answer. Right. Alhamdulillah. Okay, let's look at another scope of this topic, which talks about energy. Number 1, we have only 2 types of energy, and energy will interchangeably change between these 2 types of energy. Number 1, since it's in motion, keep moving to the left, to the right, or up and down, then it possesses kinetic energy. And another is what we call as U, potential energy of the spring. Potential energy belong to spring. Okay. Now, of these 2 energy, all right, 15.19, 15.2, try to conclude the expression. So, I'll straight away focus on the main issue. Okay, not derivation. Now, the energy, okay, the energy can be written in 3 form. In 3 form. This is number 1. Okay, number 1. This is number 1. This is number 2. Okay, this is number 1 just now. And there was another. Okay, that was this. Okay, remember this expression, half mv squared, kinetic energy? Only that. Okay, so when you jot down the energy form, okay, you will find that, oh, the energy can be calculated by 3 means. 3 cara, 3 techniques. Half K A squared. All of a sudden, why is this, madam? Okay, have a look. Okay, this one. It's by means you will arrive with the same answer. Second methods. Alright. And the third methods is supposed to like a 3 long expression connected to one another. I don't have the enough space here. So it should be half m v squared plus half k x squared. Okay, before we go further, we need to understand first why there are 3 expressions. And for that reason, let's have a look here. Okay, energy. Okay, hopefully this helps. Okay, that's this energy, right? Okay, I was trying to make this larger. Just does not help. Okay, alhamdulillah. Okay, larger now. Okay, play. Alright, okay. When the object is at 0, okay, listen carefully, the velocity would be at the maximum. Hold on. Okay. When is the velocity at the maximum? when the displacement is 0. How about velocity turns to be 0? Velocity would be 0 at maximum amplitude. No, sorry. Maximum amplitude is double words, double strong. Amplitude represent maximum displacement. Right. So, okay, listen to the analogy. Remember when you learn in free fall, when object being thrown upwards, when it reaches the highest displacement, highest y, what happened to the speed? Momentarily, it turns to 0. So same as this object. So relate to that, it's much easier for you to memorize. So object would turns when object in simple harmonic motion, velocity would be 0 when it's at the maximum displacement at A. Right. Okay. Now let's jot down somewhere. Okay. At the amplitude, what happened just now? V is 0. Okay, V is 0. At x equivalent to 0, what happened just now? V is at the maximum. Okay, that's the essence. Let's get back. Oh, it doesn't go full screen. All right, what happened to the acceleration? Acceleration is much easier to digest because acceleration here very similar to the displacement. Acceleration is this 0, displacement is 0. Acceleration maximum but negative value. Displacement is maximum, right? Why? Because this concept. I'm using red pen because somehow the idea of acceleration will be a bit different. Acceleration max is actually at um, no. X acceleration is proportional to the x, and therefore you find that A max then occur at A, right? A mean, which is 0, occurs at x equivalent to 0. Okay, easy to understand, yeah? Right now, let's get back. Okay, we are talking about energy. We haven't yet reached there. All right, okay. Now, from there, when we try to relate with the concept of kinetic energy, then it only makes sense that when the velocity is at the maximum value, energy is fully converted into kinetic energy. And that's what we are trying to portray here. Look at the orange color. Okay, orange color. So velocity at time 0 is at the maximum value, and you find that kinetic energy is portrayed to be the largest, and this like this. Okay, so look at the energy kinetic is at the maximum while the potential energy U is 0. U is 0. Okay, now that we are there, at least okay, hold on. So therefore here we see is that the kinetic energy is maximum at displacement 0, while here at equilibrium kinetic energy at the amplitude kinetic energy will be minimum value because of the velocity 0 or speed 0. Madam, why did saying sometimes you did say speed, sometimes you say velocity? Speed is considering only the value, but if you follow through the expression, especially that involve the t function, time function, so you find that you will arrive with the velocity, right? And object is like motion there to the right, to the left, to the right, to the left. Therefore, there is direction involved in this case, including up and down. Okay, in that sense, now that you understand where velocity would turns out to be zero and such, you can now connect with the idea of the potential. Then it should be the high at the end. If someone is being poor, then somebody would be rich. Who? The potential energy would be maximum. While if velocity is at the maximum value, kinetic maximum, then potential energy just become minimum. Does it make sense? Okay, right. So maximum. Okay, now the potential energy is the expression that I have shown you much earlier, which is half K, which is like, this is supposed to be X squared, and this is 0. Okay, now you can see the correlation. While here is half K A squared. And that's the reason why I did mention, if the question asking you what will be total energy, you don't need to use that long expression just now. You can straight away use half K A squared. Then you get the total energy. Or half mv squared, just ensure that V is maximum. Okay, you get the total energy. Alright, so total energy half Ka squared or half mv squared. Or if it's not at the amplitude, neither at 0, then only you use the combination. The combination where, in that sense, it's combined together. Alright, hold on. So when it's neither, for instance here, okay, here I can, somewhere here, somewhere, okay, let's just give times. Here, okay, at what? This is pi. This is pi over 2, pi over 4. Okay, pi over 4 pi over 4. Apa pi over 4 tu madam? Okay, one cycle 360 2 pi, divide by half is pi, divide lagi another half is not pi over 2, so pi over 4 is here. So when it's at pi over 4 here, displacement is neither at the 0 or neither at the amplitude, then only you use this expression. Where's the book? This expression. Please use this expression. Okay. So let's add some notes here. Use when x not a or 0. Okay. Alright, let's have a look. Okay, we have seen this graph before. Alhamdulillah. Okay, this is two notes in terms of the idea of the velocity, the energy. Okay, look at this A figure. Okay, A figure. It is at the maximum amplitude, and therefore look at the potential energy maximum. Kinetic becomes 0. Half mv squared is 0. Okay, at the highest end, at the largest displacement. And at where equilibrium, this is equilibrium, x equivalent to 0. So you find that the energy now is kinetic energy is fully. Kinetic energy is full. Kinetic energy is full. But yet in terms of the value, dia full. Full Ke. Okay. But it's also equivalent to half Ka squared because it's values. Because values. Okay. You can either calculate in such. And the last one, neither 0, neither A, you find that, a mixture of energy. There's some in form of kinetic, some are in potential energy. And this is when you will choose this expression. Alright. Now, to go here, remember just now the expression, if you know the velocity, then you can use this equation, half mv squared, but ensure that v is maximum velocity, maximum speed. Alright, let's have a look at example 15.3, where whatever we have seen just now, we are going to use in this expression. So in this example, 0.5 kilogram cart. So this is the mass connected to a light spring with force constant 20 Newton. Alhamdulillah, frictionless horizontal air track. Use energy approach to respond to question below. Okay, hold on. What is 20? Okay, madam. 0.5 kilogram cut. Cut, madam. Why cut? So that it's easily oscillate. Okay. If 0.5 kilogram, imagine you have gula, sugar, 1 kilogram, cut it into half. Okay. So it's very large. And therefore, oscillation would not be easy as compared if you put a cut. So this is a mess. And if calculate maximum speed, if the amplitude is 3 centimeter. So this is our A value. Maximum speed. Okay. Now what we did just now, okay, we make comparison. Okay. I'm aware that we have another third expression that it could be like equivalent as well to half kx squared plus half mv squared. But choose only this portion. Okay. Equal with one another because they are equal to one another. Why? Because they are equal. Their value are equal to one another. Okay. If here is 9 joule, then here is 9 joule. So half Ka squared is equivalent to half mv squared. Simplified, you will arrive with the answer. What will be the velocity? Let's look at B. Velocity of the kite when position is 2 centimeter. Alright, what is 2 centimeter? Alright, 2 centimeter is actually less than A. Less than A. So when it's less than A, use this expression. Okay. Now, this expression is simplified. I would rather you memorize it in the form of the original form, which is half Ka squared is equivalent to half Kx squared plus half mv squared. Then rearrange. Okay, I'll help you fill up this. K is 20. A is 0.003 meter. Okay, and this x is 2 centimeter. Mass, which is 0.5. Alright, so indeed, if you follow with this my equation, you will arrive similar answer as this one. So plus minus. Don't worry about the plus minus, okay? So basically, if you just left your answer 0.141, it's correct, right? Compute the kinetic potential energy of the system when position of the cut is 2 centimeter. So the question asking you, okay, please calculate kinetic energy, calculate potential energy. Alright, so the kinetic energy, look at how they calculate. It's half mv squared. The v use this value from the previous because 2 centimeter is velocity that you have calculated, okay, from B, right? Then you will arrive with 5. Kinetic energy is half K and then X, okay? So 4. Now adding these two up is 9 millijoule. Now, I like you to give a try half K A squared. Now, this A is 0.003 squared. You will indeed arrive with 9 millijoule. So this is what I'm trying to say from the very beginning, that total energy is 5 millijoule at the amplitude at the x equivalent to 0 equilibrium. Same value. And as well equivalent to at 2 centimeter, which less than amplitude. Their energy is conserved. It's just interchangeably changed. So sum of kinetic energy equal to the total energy. Alright. Okay, what if? Okay, let's just give it. Alright, where are we just now? 15.3. Okay, I'm about to move to the next one. 15.4. Alright, 15.4 is the part where we're going to see how we get the value for 5, right? How we are going to get 5 value. Alright, this is a situation where there is this turntable. Turntable means it's able to rotate but in a vertical motion. And then there was this light up there shown onto this turntable. And at the end of the circumference, they embed a bit, and therefore there will be shadow portray at the screen on the table, and you will be able to differentiate the movement of the table to the right, to the left, to the right, to the left, mimicking simple harmonic motion. So this is what the experiments are all about. So it demonstrating connection between simple harmonic motion and the circular motion. I have actually discussed this a little bit from the very beginning using different style. Now, okay, what I want you to see is you'll find that this picture shows okay, to the right. All right, this figure is not related. Okay, so at t equivalent to 0, object is at positive amplitude. Okay, since it's at positive amplitude, this expression 5 there will turns out to be 0. Understand? But then again, this figure try to portray the idea of the amplitude, yeah, where it's half, somewhere in between. Okay, you have to divide into half. Okay, right. Let's have a look. This figure, okay, is actually the same correlated to this figure, but okay, let's say that the experiment does not start at the amplitude. It start at, as what you seen here, when t is equivalent to 0, there was this angle. Okay, means that the shadow somewhere less than amplitude, less than amplitude. Okay, now what is this? Okay, this is when you have to make correction to the equation, and this correction is called as 5, and the term used, it says that the phase constant 5 for simple harmonic motion correspond to the initial angle that makes with x-axis, right? So initial angle. All right, okay, wait. Look at this quick quiz, yeah? Okay. The ball in figure 15.13 move in a circle of radius 0.5. So radius 0.5 is now the amplitude. Why, madam? Okay, look at here. This is the radius, which is 0.5, and therefore 0.5 becomes the amplitude. Okay, 0.5 is now the amplitude. Hold on. So this is the A. At t equivalent to 0, the ball is located to the left side. To the left side. So at t equivalent to 0, it's not here to the right. It's here. It's here. Okay. It's here. Okay, it's here. It's negative. So if I were to sketch the graph, okay, the graph would look something like this. Because it's at time 0, it's negative A. So negative 0.5 meter. Alright, understand? Okay. Now, what are the correct value for amplitude and phase constant? And phase constant. Alright, now. Okay, I'm gonna help you by this figure. Remember that the whole from here to here is equivalent to 2 pi, one cycle, 2 pi, and therefore dividing it into half would be pi. Okay, right. I'm start here. And then here would be all right. Okay, good. Let me sheet. Okay. Now, do you notice something that if if the correction is not made, if what we learn in our class, if it's just omega t without the correction, then the graph should be starting here, right? Okay, but because it's here, there was this additional thing this additional thing, where this additional is actually equivalent to 5. Additional is equivalent to 5. So that's the reason why the phase angle is equivalent to 5. The answer is this one, C, yeah? So 5. So because of this one, okay, notice that the difference that it makes with the original A at positive A is this, pi. And that's the reason why the angle is measured as pi, one technique, okay? And another is, how do we know what we should be using? Is it plus or is it negative? Okay. One technique is, you can on your own, take your calculator, substitute that t is now 0. Okay. Therefore, left with only either cos negative pi or cos positive 5. Alright, I need you to use your calculator, turn it into radian mode, punch cos negative pi and cos positive 5. Okay, you will find that the answer should be, which one? Should be negative. Cos, okay, let me just double check. Cos negative 5, negative pi, sorry, negative 5 is negative 1. Negative 1. And negative 1 times with the A, which is 0.5, we will arrive with negative 0.5. So that's how you decide that it's negative. So it should be omega t minus pi. Okay, omega t minus pi. Okay, I just jot down the final answer here so that you understand. X is now A cos omega t minus pi. Okay, nevertheless, the question is just asking you constant, phase constant, so definitely just pi. Right, let's look at example 15.4. Circular motion with constant angular speed. Alright, this example will tackle this quick quiz again. Now, figure in 15.13, rotate counterclockwise in a circle of radius 3 meter. Constant angular speed 8, and at t0 its shadow is 2 meter and is moving to the right. So this radius is now the A value. This 8 rad over second definitely is omega. And what is this? This is x at t0. Okay, at t0. So determine x coordinate with a function of time. So they want the equation. So notice that the shadow is not at the maximum position, which 2 is not 3. It's supposed to be 3, but it's 2. So in this sense, there is 5. So therefore, let's find this 5. How much is this? So what is the technique? Innalillahi wa inna ilaihi raji'un. Okay. How do we find it? Okay. When we try to simplify 5 or we try to substitute value. So this is 3 meter. This is 2 meter. Omega is just now 8. Is it 8? 8. Then as you simplify, you will arrive, remember, radian mode, with this answer 0.841 rad. This is the answer, not this one, right? 0.841. However, you are not so sure whether it's positive or negative. Therefore, you have to try sub t0 to the equation, and therefore your equation would be x equivalent to 3 meter cos what, z plus minus 0.841. Okay, 0.841. Alright, your task is by using your calculator, if it's cost positive 0.81, what will be the answer? If it costs negative 0.841, what will be the answer? Alright, okay, now. So you will find that if you take positive, then the shadow should be moving to the left. Okay. If you choose negative, okay, uh, sorry, okay, and the word itself has been there. The whole statement is just there, okay, and therefore, okay, you are considering that 5 should be negative 0.841. Okay, that's how you decide that it's a negative, right? And it's moving to the right, and it's moving to the right. Okay, let's look at the next question. Find the x component of the shadow velocity and acceleration at any time. Alright. Have a look again the x value, the x expression. X is 3 meter cos 8t minus 0.841. And, okay, you do dx over dt like what they did just now. Cos becomes sine, okay, and 3 meter times 8, so negative 24. And remember, cos is when d cos over dt would turns out to be sine, negative sign. All right, and it goes the same with a. All right, it goes right. Okay, thank you.